Now, after distance, speed, the next quantity, the next physical quantity which is important for us to discuss here when studying motion is acceleration. So simply acceleration is how is your speed changing with time, or how is your velocity changing with time. So the acceleration is a vector, alright, so it should be the change of your velocity vector over change in time, and it should have the same direction as the change in the vector of the change in velocity. Usually, most of the time, we don't really care about the vector, the acceleration vector, so we can just write the magnitude of the acceleration vector as the change in speed over change in time. Because then, since we're talking about acceleration here, just the magnitude, this can be just the change in speed, not change in the, obviously it's the magnitude of a vector as well, right? But you have to calculate the change in speed. Most of the time when we're dealing with problems in which the acceleration is going to be expressed as this one, we are not really caring about the direction. So both velocities, they will be one-dimensional, so either going backwards or forwards. So the only thing that we have to worry about here is the sign. If it's positive, you're going towards your positive reference frame, and if it's negative, you're going towards the negative, right? So, well, as simple as that. So let's cover one example. Let's say that we have so we have a train. That's a Japanese train. That's the N700. So this is its acceleration. This is seconds to the power of 2. Okay. Now, how could we calculate the time for it to reach its maximum speed, assuming that the maximum speed is this 300 kilometers per hour? Well, so what would be, if we're talking about a train which is going to start its movement, it's going to get to 300 kilometers per hour, what would be its initial speed? Well, it's 0. It's at rest. So 0 meters per second. Our final speed is the maximum speed we're looking for, which is 300 kilometers per hour. So we could even write this as 0 kilometers per hour. 0 is 0, right? Unless we're talking about temperature, Kelvin, and some other conversions. Here, it doesn't matter kilometers per hour. If you're walking 0 meters per second, it's 0 kilometers per hour as well. Now, we're looking for the change in time, our elapsed time, which would be our final time minus our initial time. However, if we assume that we start counting at 0 seconds, that's simply our final time, and we can just call it time. Does it make sense? Should. So, acceleration is change in speed over change in time. So in this case, it's simply v over t. That's our final speed, because it would be v minus u, which is 0, and final time minus initial time. So v over t. So that's 300 kilometers per hour over time, and that is our acceleration, which is 0.72 meters per second squared. So if we want to calculate the time, we would have to swap those. So it would be 300 kilometers per hour over 0.72 meters per second. So now we have to watch out, because we've got things in different units. We'll have to convert everything to the same unit. So what I'm going to do here, I'll just recalculate 300 kilometers per hour in meters per second. So that would be around 83.3 meters per second over 0.72 meters per second squared. So if you look at the units now, we'll be able to cross out meters, cross out one of those seconds to the minus 1, and we'll have here 1 over second to the negative 1, which will be second. right? So 83.3 divided by 0.72 is going to be 116 seconds. So it's almost 2 minutes. Now we have described motion using graphs when we're dealing with distance time graphs, but also we can describe motions of velocity with time as well. So take a look at this graph. We could describe this motion. We could try to, I don't know, try to interpret what's going on. So it starts with a constant speed. No. If this was a distance time graph, then this would mean a distance speed. But since this is a velocity time graph, the velocity is getting larger and larger. So when we reach here 10 seconds, our velocity has gone from 0 all the way to 4 meters per second. So this line now means that there is an acceleration. The velocity is changing. So in this case here, there is an acceleration. Now when we see this flat line, the velocity is not changing while time's passing. So that basically means that we're constant velocity, right? If this was a distance time graph, that would mean that we're not moving at all. But since this is a velocity time graph, this means that we are not changing our velocity. Our velocity has reached the value of 4, and it's not going to change. Now, in this moment here, our velocity quickly decreases, and you can see since this is one rectangle and this is two rectangles, it's decreasing twice as fast as here, as it was rising here. So it has stopped quite abruptly. Here, it's a flat line again, so the velocity is not changing. Besides, it's 0. So it has stopped, right? It has decreased its velocity and stopped. Then we get a negative velocity, so that means that it's going backwards and accelerating. Here it stops accelerating and moves at a constant velocity of -3. So if our positive reference frame was to the right, it would be going left. And here it slowly decelerates until it reaches 0 velocity. So slowly, that's the smallest acceleration in absolute values, right? So magnitude wise, that's the smallest one, the lowest one that we have in this graph. So there are two pieces of very important information that we can get from this graph. So if we get the gradients, they're gonna give us the acceleration, and that's really important and quite good. So for each of those segments, we could calculate our acceleration. So here, between 0 and 10, let's again split this into different sections. Let's call this 2, 3, 4, 5, 6, and 7. So at point 1, we have acceleration. Now, we're going to get the gradient, which is rise over run, but if you notice, rise is velocity, is changing velocity, and run is changing time. So it's exactly the same thing. We're actually doing this. We are, when we get the gradient. Alright, so if we get the gradient here, that would be rise 4 and run 10. So that's 4 meters per second in 10 seconds. Notice what this means. It's a change, it's an increase of 4 meters per second in its velocity in 10 seconds. So what would be the acceleration? 0.4 meters per second squared. Number 2, well, acceleration is change of velocity over change of time, or you can get the gradient. If we get the gradient, it's a flat line. And change in velocity is 0. The velocity here and here is the same. So that's 0. Point 3. We are decreasing, so we should have a negative acceleration. But let's see. So it's going to be change of velocity over change in time. So our change in velocity is final velocity minus initial velocity. And here, when I say final velocity, is just between those 2 points that we're observing on this part of the motion. Okay, so final velocity here would be 0, and initial velocity would be -4. And change of time, so time here would be 50, and here would be 45. So 50 minus, oops, let me put the final time and initial time. And then final velocity would be 0, initial velocity would be 4. I will not write the units, but you know that it's meters per second. Everything is in meters per second and seconds, so I don't have to worry that much. So final time is 50 and initial time 45 seconds. So that would be 5, -4. So -4 fifths, which is -0.8 meters per second squared. And that's what we observed before when I told you, when we observed this motion here, we're going to get this acceleration to be twice as large as this one, but negative, and that's it. We have found exactly 0.4 and 0.8, but this one is negative, so it matches what we thought we were going to get. Now number 4, again, acceleration change of velocity over change in time, so it's 0 because there's no change in velocity. Number 5, we are going down again, so our acceleration, I'll just put the numbers now straight away. So number 5, we are going to 70 seconds from 60, and our height, we are going from 0 to -3. So -3 minus 0. Final minus initial. So that would be -3 over 10, which is -0.3 meters per second. Sometimes IB questions, they ask you to calculate those speeds, those velocities, and compare them to tell when was the smallest acceleration. In this case so far, that would be the one. Now, number 6, fair enough, acceleration 0 because change of velocity is 0 again. And number 7, rise over run. Now we're going up, so we expect to have a positive number. So our final run is 0, and then minus, what was our velocity before? So over here our velocity was -3, so 3. Here it's final time, which is 120 seconds, minus initial time, which was 90. So it's 30 seconds, and it's 3 meters per second change in 30 seconds, right? So we could even, it's 1 over 10, so that's 0.1 meters per second squared. Alright? Now there's also another piece of information that we can get from this graph. Despite the gradient, so despite the acceleration, we can actually go backwards. Now, if you notice, here we have velocity and time. So if we actually got, let's say, an area here, we would have to multiply something here by something here, right? So some velocity by time. And what should we get unit-wise when we multiply velocity and time? So velocity is measured in meters per second and time is measured in seconds, so we should have some displacement or some distance, and that's what we're going to use now. So let's change this graph a bit. Now it's exactly the same graph, and if you notice, I've calculated some of the areas here, so we could close a triangle here and calculate half of its height times base. That's the equation for area of the triangle, or you could even use some more sophisticated equations for those areas. It doesn't matter. Usually the simplest is the best. So if you were asked, okay, what's the total displacement? How much, how far has this person, this object, how far is it from the original position? So we would have to analyze if our area is above the graph, it will be positive since it's going forward. And if our area is under the graph, then we'll subtract it since it's negative, so it's going backwards. So let's see. Let's calculate the areas. So we'll have here area. Oops. So we'll have here area 1, area 2, area 3, area 4, area 5, and area 6. So let's work each one of them out. So area 1 is given, that's 20 meters. If we multiply a half by 10 and 4, so 10 was our time, 4 was our height, so if multiply those would be 20. In this large square here, we have a difference of 35, and the height is 4, so it would be 140. Alright, 140 meters. Everything is in meters and seconds, so meters. Area 3. Now area 3 is a triangle again, and it's given. And take a look, it's half the area. That's interesting, isn't it? Now A4, A5, and A6. So that's the ones that we're going to do now. So this area A4 is a triangle with base 10. So it should be 10 over 2, and the height is 3. So that's 5 times 3, which is 15 meters. A5 is a rectangle. Height is 3. Oh, here, if you consider height to be negative, right, it would be negative 15. I'll put the sign here just because it's going to show us that it's actually a negative displacement, so we're going backwards. Well, A5 here, it's 3 times 20. So that's negative 60 meters. And the last one, we're going from 90 all the way to 120, so this base is 30. And this height is 3, so that's 3 times 30 divided by 2, so that's negative 45 meters. Here again, if you put the negatives, just because this would be negative, right? The velocity would be negative. So if you just keep the signs, you will have negative areas, which are awkward mathematically. It doesn't make sense, but here physically they will make sense, because the total area, so if we sum all of those, so we take those positive, we take those negative, so it would be 20 plus 140 plus 10 minus 15 minus 60 minus 45, right? So that should give us 50 meters. And that's the total displacement. That's the total distance. Well, not the total distance in this case, because this person or this object has moved further and then has come back. So we are talking about displacement now. So it's just how far are you from the beginning point. Alright?